We now cover these two topics, attenuation in rectangular waveguides and attenuation in circular waveguides. We start with formulating the attenuation in rectangular waveguides. We will restrict our discussion for the dominant TE10 mode only, and for TE10 mode we have seen the longitudinal Hz is given in this form and we have the transverse field component Ui and Hx. And Ex, Hy and Ez equal to 0. Now, we can calculate the power flow inside the waveguide as half real part of E cross H star is the Poynting vector and then dot the area dx dy and Az is the unit vector for this elemental area. So, if we evaluate this expression, we get an expression for the power that flows inside the waveguide because of the dominant TE10 mode, and this can be written as omega mu a cube b by 4 pi r square real part of beta and A10 magnitude square. Please note that when the wave will propagate inside the waveguide, beta will be a real quantity. Now, let us see what causes attenuation inside the waveguide. We have calculated the field components inside the rectangular waveguide considering the walls to be perfect conductor. In practice, these conductors will have finite conductivity and a small amount of power will be lost on the metallic walls of the waveguide. Further, another source of attenuation is because of the loss in the dielectric media filling this waveguide. For the time being, we are assuming this dielectric inside the waveguide to be a perfect dielectric, it does not dissipate any power. Now, how we calculate the power that is lost on the waveguide walls? This power loss per unit length due to finite conductivity is given by PL is equal to Rs by 2, C is the contour and J magnitude of surface current squared into dl. Now, where from this surface current comes? We know from the boundary condition that the magnetic fields for TE10 mode, that means Hz and Hx, they will be discontinuous on this metallic boundary and we can calculate the surface current that is induced on the walls of the waveguide by n cross h. Rs is the wall surface resistance and C is the contour that encloses the inner perimeter of the waveguide walls. Now, once we are able to find out Js, we can evaluate this integral and this will give us the power loss per unit length, and from there we can find out the attenuation constant. Now, the surface currents will be present in all the 4 walls, but from the symmetry the currents on the side walls will be identical, and similarly the currents on the top and bottom walls, their magnitude will be the same. And therefore, what we can do, since we are evaluating mod j square, we can evaluate only on two walls and multiply this by 2. The surface current on the left side wall is given by Js is equal to n cross h evaluated at x is equal to 0. Now, if we look at the expression of the field component, then H x becomes 0 at x is equal to 0, since the H s dependence with x is given by sin pi x by a, and therefore, at x is equal to 0 it becomes 0. So, on the x is equal to 0 wall we have only H z, and the vector that is perpendicular vector to this wall is A x, and therefore, we can write the induced surface current to be equal to minus A y A 10 e to the power minus j beta z. Similarly, surface current on the bottom wall is contributed by both H x and H z component, and for the bottom wall the unit normal vector is A y, and therefore, once we evaluate this expression A y cross x H x at y equal to 0 plus A z H z at y equal to 0, and substitute the expression for H x and H z, then we get this as the surface current on the bottom wall. So, once we have the surface current densities calculated on the top and the bottom wall, and then we can utilize this expression in calculating the power loss per unit length. So, now we have the JSY, JSX and JSZ, these current densities are as given, and therefore, if we substitute these quantities, then we get and evaluate this integral, we get the expression for power loss per unit length on the waveguide walls, and this is given by R s mod A 1 naught square B plus A by 2 plus beta square A cube by 2 pi square. Now, this is the power loss per unit length, and the attenuation constant is given by power loss at z is equal to 0 divided by 2 p naught. Now, this p naught here we have already computed, this p naught here will be the power of the dominant T 10 mode which we have calculated, and therefore, if you substitute these expressions, then we get an expression for the attenuation constant alpha. Now, further simplification is possible by considering that omega mu can be written as omega root mu epsilon into root mu by epsilon, which is equal to k eta. Eta is the intrinsic impedance of the dielectric, and once we substitute that, we get the equation of this form. Now, for T10 mode, the cutoff wavelength is lambda c is related to cutoff wave number k c as 2 pi by lambda c, and lambda c is 2 a. So, k c can be written as pi by a, and we know that beta square is equal to k square minus k c square. So, if we now substitute this beta square by k square minus lambda by a whole square, then expression for alpha becomes as shown here, and on simplification it becomes alpha equal to R s 2 pi square b plus k square a cube divided by k eta beta a cube b. So, this is the expression for the attenuation constant in a rectangular waveguide. We can put this attenuation constant expression, starting with this expression, we can, if we take this a cube outside, we can put the equation for alpha in this particular form, and we find that for a T10 mode type propagation, this factor K A can be written as pi f by f c, and therefore, alpha can be written as R s k divided by beta eta b 1 plus 2 b by a f by f c whole square. So, here in this particular expression we have expressed alpha in terms of the operating frequency and cutoff frequency. Please note that attenuation constant is a function of frequency, and f is greater than f c. Here of course, we will have another frequency dependent term which is beta. So, in general, as the frequency of operation in a waveguide is varied, the attenuation constant changes. Please note that our entire derivation is based on the fact that the attenuation on the waveguide walls are very small, and we have computed the surface current density in terms of the field components H x and H z, which were evaluated considering that there is no attenuation on the waveguide walls. We have seen how we can calculate the attenuation constant for a rectangular waveguide which is propagating T10 mode, and when we consider only the losses in the waveguide walls. Now, let us try to find out the attenuation constant in a circular waveguide in the similar manner. So, we will restrict our discussion to the dominant TE11 mode in the circular waveguide, and as before we will assume that the dielectric region within the waveguide, this is lossless. Whatever attenuation takes place, that is because of the power loss in the waveguide wall. So, while calculating the different field components for a circular waveguide, we have seen the phi dependence of the field can be written as either sin n phi or cos n phi, and in general it is given by A sin n phi plus B cos n phi. Now, let us consider that B is equal to 0 and we write the field components for the TE 1 mode, that means n is equal to 1. So, we can write Hz as a function of rho phi and z as A sin phi j 1 k 0 e to the power minus j beta z. And once we have written Hz in this manner, we can find out the E rho component. It is only a substitution of Hz here and finding out the derivative with respect to phi. Similarly, we can find out E phi component by substituting Hz and finding the derivative with respect to rho, and similarly we can find out the magnetic field components H rho and H phi. So, once we have all these field components computed, now we can find out the power that propagates along the circular waveguide for the dominant TE 1 mode. So, the power P naught can be written as half real part of E cross H star is the Poynting vector, and then integrating this Poynting vector from rho equal to 0 to rho equal to A and phi is equal to 0 to phi equal to 2 pi. And this is the unit area as at rho d rho d phi, and once this is expanded, we find that the power can be actually computed in terms of E rho, H phi, E phi and H rho, and we can substitute the expressions for E rho, H phi, E phi and H rho from the already found out expressions, and once we do this substitution and do some simplification, then we get the power P naught for the TE 1 mode is given by this expression. So, as before, once we have found out the power for the TE 1 mode, now we proceed to calculate the power loss on the conductor walls per unit length, and that can be found out as R s by 2, phi is 0 to 2 pi mod of J s square, where J s is the current induced on the circular waveguide wall because of the tangential magnetic field components. So, mod J s square A d phi, and this can be found out in terms of H phi and H z square. And once we substitute H phi and H z, then we get this expression for the power loss per unit length of the circular waveguide. And once we have P L and P 0 evaluated, we know that attenuation constant alpha c, it is given by P L by 2 P naught. So, we substitute P L and P naught from these two expressions we have just derived, and after doing some simplification we get alpha c as shown in this expression R s k c to the power 4 a square plus beta square divided by eta k beta a, and then this is p dash 1 square, which is the first root of the derivative of first order Bessel function minus 1. So, once we have this expression, we can, for a given frequency and waveguide dimensions, we can find out the attenuation constant alpha c, and for a given length of the waveguide we can then calculate by how much the power will get attenuated as it travels down the line. So, in summary, in this module we have covered the waveguides, rectangular and circular waveguides. We have seen the wave propagation in this type of waveguides, and we have studied what are the different modes which occur, and we have seen which one is the dominant mode when it comes to a rectangular waveguide and a dominant mode in a circular waveguide. We have also seen how we can calculate the attenuation in the waveguide considering the finite conductivity of the waveguide walls. So, this gives a comprehensive treatment on different aspects of wave propagation in waveguide. In the next module, we will start our discussion on microwave networks and particularly scattering parameters, which are very much useful in designing microwave circuitry.